Alright, Gen Chem Nation, in this module we are getting into gases and gas law. And so just some little tidbits about gases. They're easily compressed. Remember, there's lots of space. Between gaseous molecules. Their molecular motion is random and dynamic, so they're basically flying all over the place. Gases basically fill the volume of any container. Producing a homogeneous mixture. The kinetic energy of gases is temperature dependent. Increases with increasing temp. And molecular collisions are treated as purely elastic. Kind of like, rubber balls bouncing off of one another. Gases are measured, and you could say characterized, by units of pressure. We tend to see that in atmospheres. Or we see that in millimeters of mercury. There are other units of pressure, but that's what we tend to see. We also have units of volume. And so we would be in terms of liters for that. We have temperature. And we would need to be in Kelvin. And really, because there's no negative temp in the Kelvin scale, that might have implications on a negative pressure or a negative volume, and that's impossible. So we want to have that temperature in Kelvin. And then lastly, moles. And we tend to give this little n moniker for our moles. So those are the units that we'll be working with trying to characterize these gases in this module. Under the same temperature and pressure equal volumes of gas contain then the same moles of gas. So there's an inherent relationship between all four of these that we're going to find. And so, for instance, at STP, no, that's not Stone Temple Pilots, that's standard temperature and pressure. We would be here now at a temperature equal to 273 Kelvin, and our pressure would be equal to 1 atmosphere. 1 mole of gas occupies 22.4 liters. So that's just that inherent relationship above, that if we're under the same temperature and pressure here at STP, we're at the same temperature of 273, we're at the same pressure of 1 atmosphere, right? Equal volumes of gas contain the same volume of gas. So if I have two gases, different gases, both at 273, both at a pressure of 1 atmosphere, and they occupy 22.4 liters, then I know I have 1 mole of gas. So those are the units of gases and how we describe them. So next step is let's get into actually talking about the relationships, because what we're going to find is that all these different ways to characterize, such as pressure and temperature, volume, moles, etc., are all actually intertwined and very much related to one another. So let's talk about those relationships with the simple gas laws. And we have quite a few of these. The first one is Boyle's law. And basically what Boyle, found is that, pressure is proportional to 1 over volume, or the inverse of volume. And so if we are, at constant temperature and moles, then we have we have this simple relationship. Between pressure and volume. So P1 V1 equals P2 V2. So we have here, pressure, and we have volume. And we could say these are for conditions 1. And then we have, the same thing on the other side as far as pressure and volume. But now these would be conditions 2. So, as long as temperature and moles are constant, if we change the pressure, we change the volume. And this is much like a balloon, if you think about it. Like you fill a balloon with gas, there's constant moles within the balloon. It's at constant temperature. And so if you push on the balloon, right, if you try to shrink the volume of the balloon by pushing on it, you're increasing the pressure, right? And so there's that inherent, relationship between the two. Smaller volume, greater pressure, or greater volume, less pressure. Take a look at this example of this pressure-volume relationship with this little demo video. Take a look. So in this Boyle's Law demonstration, what we will have here is a balloon that's trapped in a gas in a vacuum container. And what we're doing is pulling the air out of the container with that red rubber hose at the bottom. As we decrease the pressure, pull the air out, the volume of the balloon expands. So there's that pressure-volume relationship. And then as soon as we then increase the pressure by making it go back to atmospheric pressure, we're going to see the balloon shrink, which is what we're seeing now. So we have that inverse relationship between pressure and volume. Another probably cooler way to look at this is with our little Easter ducks here. Oh my God, it's alive! But this is a marshmallow, right? So it has gas within the cream, and so it can expand and contract just like a balloon can with that idea of pressure. Here's shaving cream. Shaving cream again is a foam, basically gas trapped in a solvent, if you will. And so here, reducing the pressure, we see that volume of the gas expanding with the shaving cream getting much larger in volume. So that's Boyle's Law, the inverse relationship between pressure and volume. Let's look at an example of Boyle's Law. So our question is thus: what is the pressure that will result if 3,000 liters of oxygen gas at 0.8 atmospheres is compressed to a volume of 15.0 liters? Now, as far as a prediction, we would expect the pressure to increase, right? Because we're talking about compressing a gas. And that's happening by shrinking the volume. So that's what we kind of expect. If we look at, some of the information that's given to us, we have, this volume of O2 and we have a pressure. So there is our, kind of first set of conditions, our V1 and P1. So we could say our volume 1 is 3,000 liters. We could say our pressure for those conditions would be 0.8 atmospheres. And then if we continue on, we're asked, what pressure? Well, now we're compressing it to a volume of 15.0 liters. So our volume 2 would be the 15 liters, and then really it's the second pressure that we're trying to figure out. Since there's no mention of temperature and moles, we must assume these are constant. So sometimes they just don't give you all of the information, and so we can't bring extra information into the question. We just must assume that those are constant. And so that allows us now to set up this simple relationship between a set of initial conditions, P1V1, to then our second set of conditions, which would be P2V2. And so we can just, basically plug these values in. We had our pressure of 0.8 atmospheres, that volume of 3,000 liters. We have the second pressure, which we're trying to figure out as a result of the compression from our 3,000 liters to our 15 liters. And we end up with a pressure equal to 160 atmospheres. And notice that this is an increase in pressure as we predicted. Right? We predicted that since it's compressing, our pressure should increase, and that's exactly what we have determined here. Now it's just a simple conversion between the units of atmospheres and millimeters of mercury. So the conversion there is, 1 atmosphere is equal to 760 millimeters of mercury. And when we do that, we get a value of 1.20 times 10 to the 5th millimeters of mercury. So that's the simple relationship of Boyle's law, looking how pressure and volume are directly related to one another, so long as we keep these other two possible variables constant, namely temperature and moles, keeping them constant. The next law is Charles' law. And Charles' law basically talks about, a direct relationship between volume and temperature. So but we have to remember to keep the other things constant. So as long as pressure and moles is constant. So that's Charles' law, just throwing another, simple relationship our way as far as this idea of volume and temperature. Something closely related to it would be Monson's law. Monson often gets thrown under the bus here, not really mentioned, but just basically taking the same type of relationship, but now instead of volume, relating it to pressure. And it kind of makes sense because of Boyle's law. Like if we have a pressure-volume relationship, and then if we go to Charles' law, we have a volume-temperature relationship, well, then it makes sense that we probably have a pressure-temperature relationship as well. And so, we find there's the same thing, that there is a direct relationship between the two. So it's really kind of the same idea. It's just a question of whether we're talking about a pressure-temperature relationship or a volume-temperature relationship. I have a nice little demo with the volume-temperature relationship, so take a look at this demo relating volume and temperature with an oxygen balloon. So here's our oxygen balloon, and we're going to pour some extravagant amount of liquid nitrogen over it. It's like 200 degrees Celsius, negative 200 degrees Celsius. And notice that there's that huge collapse in the balloon volume as a result of that chilling effect. Now as the balloon is warming up, we now see the expansion occur again. So there's Charles' law, the direct relationship between volume and temperature. As temperature goes down, volume of a gas goes down. As temperature goes up, volume of the gas goes up. And so there is Charles' law, direct relationship. Now let's, with that one video, let's look at an example of a Monson's. So, we could talk about maybe a road trip here. So the pressure in your tire is 38 psi. That's another name for pounds per square inch. So kind of an Americanization of that term. So the pressure in your tire is 38 psi at 23 degrees Celsius. And so, we're going to head out, or you head out on a road trip. Down I-89. And basically after a gas fill-up, your tire pressure is now 44 psi. Assuming the tire's volume is constant, what is basically the temperature of the gas inside the tire? So there's our question, right? And again, we see kind of just two sets of conditions if we look at it, right? We have this idea of 38 psi at 23 degrees Celsius. So we could say that we have a P1 and a T1. And then reading further, there's a lot of fluff to the question. But we end up with now, the pressure being 44 psi. And now we're asked for the temperature of the gas. So there would be our second pressure. And really what we're looking for is that idea of T2. So if we just kind of organize that. Notice I did a quick temperature conversion there. Our pressure 2 is 44 psi, and now we're looking for that temperature 2. And so, we kind of have to say the same things. It is mentioned in the question about the volume being constant. We need to assume the volume and moles of gas are constant. Volume is mentioned in the question, but moles is not. But so we must assume can't bring that extra information into the question, so that it must not be important or it must be constant. So that allows us to use that expression for the pressure temperature relationship. And so we can just plug these in. The nice thing about pressure and the simple gas laws is that as long as you're consistent with units, you're fine. Meaning that even though we would expect pressure to be in atmospheres or millimeters of mercury, and we have it here in terms of pounds per square inch, since the units are going to cancel out as we do the arithmetic, it really doesn't matter in this particular case. However, Kelvin is very, very important, right? Because of the idea of Kelvin not having a negative in its temperature scale. If for some reason that one of these temperatures was negative, maybe in Celsius or Fahrenheit, well, then that would imply we would have a negative pressure, or going back to Charles' law, a negative volume. So we can't those don't exist. So we must make sure that we're in Kelvin. So that's crucial to our conversion. And so we can manipulate this expression to basically solve for T2. Something like this, and our PSIs cancel out, and we end up with a value of 342 Kelvin, or basically 69 degrees Celsius. So that's the relationship of pressure and volume with regards to temperature, right? So Charles looking at the volume temperature side of that thing, of that relationship, and then Monson looking at the pressure temperature side of that relationship. And so in the fourth representation of simple laws would be, we've talked about pressure, volume, and now temperature is bringing moles into the game. And that's Avogadro's law. And Avogadro's law basically says, that moles is directly proportional to volume. So long as we have those other constants at constant pressure and temperature. So we're looking at now this expression of V1 over N1 equals V2 over N2 in that direct relationship. So let's do an example of this. A gas occupies 44.8 liters at STP. How many moles of gas are there? So here we find, that we have volume, and basically asking how much, how many moles of gas are there. So we could call this V2 and N1. And then we have to remember, kind of this idea of what STP is. Again, not Stone Temple Pilots, right? But this idea of standard temperature and pressure being, 273 Kelvin and 1 atmosphere. So remember, at STP, 1 mole of gas occupies 22.4 liters. So really there's our other two constituents, namely the N1 being, let's say, 1 mole, and our V1, which is the 22.4 liters. And so in this particular case, right, remember, temperature and pressure are constant. So that means we have this relationship between the two with Avogadro's law, the two being volume and moles. So if we plug those values in, right, we could say we have 22.4 liters occupying 1 mole, or being 1 mole of gas, and now we're at this new volume of 44.8 liters, and right, we're trying to figure out how many moles of gas is there now. So if we rearrange that, our X moles of gas would be 44.8 liters times 1 mole over 22.4 liters, or we would actually have a value of 2.0 moles of gas. So that's Avogadro's relationship simply between volume and gas. The last simple gas law is really starting to bring these together. I mean, if we think about it, we have, Boyle's law, we have Charles's law, Monson's law, and so we have this idea of combined gas laws, which basically shows, the relationship now between just not 2 things, but what three things, right? It shows the relationship between pressure, volume, and temperature of a gas, provided moles of gas is constant. So we still have that notion of something being constant. And it's really, like the name implies, a combination. Like we have this notion of P1V1, equals P2V2, right? That was, Boyle's law. And then if we wanted to bring into Charles' law, right, there was a V1 over T1 is equal to V2 over T2. And then combined with a Monson's law, now we have the P1 T1 over P2 T2, right? So all of those come together within this actual idea of a combined gas law. check out this demo of an interesting, fun experiment to do at home, showing the idea of the combined gas laws. Take a look. So here we have the combined gas law. What they have is they have this big 55-gallon drum that they have a little bit of water in, that they've been evaporating the water, and you can see the steam shooting out of the top there. So what they're going to do is they've increased the pressure within the actual vessel. They have a certain amount of moles in there, which we're going to have to assume is constant once they close the actual container. Right now they're still heating it. And so what we have now is a high temperature, a high pressure, and a constant volume. So now what they're going to do is turn off the heat, and we're going to cap the actual container, which is doing right now. And so now we have moles being constant within the equation. So now as it's cooling down, that means that the temperature is going down. That means the pressure is going down. That means that also we will see, or should see, a volume contraction as a result. Right? So there's that idea of the combined laws that are working here. So a little bit hot, so now let's just cool it all down with a little bit of water. And boom. Fun chemistry. All right, so let's look at an example of the combined laws. So let's say we have a natural gas storage tank. And these tanks actually are both compressible and expandable due to the baffles that they have within them. This allows them to deal with different temperatures and different pressures depending on what's going on. So let's say we have a natural gas storage tank that has a volume of 2 times 10 to the 6 meters cubed. And this is at 23 degrees Celsius and 1 atmosphere. Now, if the temperature decreases to negative 20 degrees Celsius, and the pressure increases to 1.12 atmospheres, what is the volume of gas in the tank? So there's our combined gas law type of equation, or question rather. So if we read the beginning, right, we have this volume that's given to us, we have a temperature that's given to us, and we have a pressure that's given to us. So we could say we have V1, T1, and P1 for those 3 values. And then going forward, we have the new temperature. We also have this idea of pressure increasing to 1.12 atmospheres, and we're asked the volume of the gas. So here's our second set of conditions with this new temperature, this new pressure, and they're asking us what is the new volume. So that's the combined gas law representation. So we have those volume V1, pressure P1, temperature T1. Notice that we did have to change the temperature to that Kelvin scale. On the second set of conditions, right, we're looking for that volume. Our second pressure has increased to 1.12 atmospheres, and our temperature is now 253 Kelvin. So important here is the temperature conversion, making sure that we're in terms of Kelvin. Again, the negative 20 degrees Celsius there would have implications in our expression here in saying that we would end up with a negative volume if we were plugging in a negative temperature. So that has to be changed. But in terms of our pressure and volume, like we got away with earlier with the Monson's law, and like we can get away with here, since the volume of the gas is not, asked of us in specific units, as long as we keep meters cubed, we can actually leave the meters cubed value. So in plugging in our representative components for 1 and 2, we would end up with, our pressure 1 was the 1 atmosphere. We were at 2 times 10 to the 6 meters cubed for our volume, and our temperature was 296 Kelvin. Our second set of conditions, the pressure increased to 1.12. We're trying to solve for that volume for the second set of conditions, and our new temperature is 253 Kelvin. So we just, need to rearrange that expression to solve for V2. You can do it stepwise, which is fine. You could manipulate it like I'm doing now. And then plug these all in and solve. So, multiplying over the 253 Kelvin, dividing over the 1.12 atmospheres, everything's canceling out here except for meters cubed. And we end up with an answer of 1.54 times 10 to the 6th meters cubed for our new volume in the storage tank. So those are all the simple gas laws. We have the pressure-volume relationship with Boyle. We have the volume-temperature relationship with terms of Charles. We have pressure-temperature relationship with the Monson. And we have Avogadro's relationship between volume and moles. And then lastly, in this example, we have the combined gas law expression. Notice in all of these, we had to keep certain things constant in order for these simple expressions to work. The simplest thing to realize is that there's a set 1 condition and a set 2 conditions in terms of the question. You're given 2 pressures, 1 volume, and you're searching for a volume. Okay, Boyle's law. So you have to look for those types of representations to then just realize that, I can invoke a simple gas law idea. All right, now we need to talk about the ideal gas law. So we already realized that there's a connection between, temperature, pressure, volume, and moles of gas. That's apparent from the simple gas laws. There is also a constant that allows us to know any of the variables. So if we think about at STP, right, which would be standard temperature and pressure, so we're at 273 Kelvin and 1 atmosphere. 1 mole of gas occupies 22.4 liters. And if we think about all the relationships that we've talked about, right, we had Boyle's relationship, which was like, P1V1. We then had, Charles' relationship, which was like V1 over T1. We had a Monson's relationship, which was P1 over T1. And then we have the ideal gas, the combined gas law representation, which is what we see here so far. And so if I put moles here, we find that this is equal to a constant. This is the Rydberg constant, sometimes called the gas law constant. And this is equal to 0.082 liter atmospheres per mole Kelvin. And this allows us to relate. So like if we were to plug all those values in, say, the 1 atmosphere, the 22.4 liters, the 1 mole, right, the 273 Kelvin, right, that's what we're getting at. And that's known as our ideal gas law representation, or PV equals nRT. So as long as we know 3 of the conditions, we know the 4th. That's kind of the idea. So if we know volume, moles, and temperature, we automatically know pressure. If we know pressure, volume, and moles, we automatically know temperature. Now there's a couple other relationships that we can find within this gas law. There is also, the molar mass version. And remember, molar mass would be grams per mole. And so we think about what moles is actually equal to in terms of solving for it, right? Moles would equal grams, not Q, grams divided by molar mass. And that's equal to N. So another version of this would be the molar mass version, where we have PV is equal to mass over molar mass times R times T. This second equation is just maybe a shortcut, if you will. It's not like we can't use the ideal gas law still, and then maybe as a second step incorporate molar mass in a conversion style. So they're really the same thing. There's also a density version. And the density version, meaning that, the density of our gas would be equal to grams over liters, right? And if I take, this expression above and manipulate it a little bit by dividing over my volume, I would get something that looks like this, with my volume in the denominator, and within that I see this idea of mass over volume, or grams over liters. And so my pressure could then equal B to the density of the gas times RT over molar mass of the gas. Right, just so that we're aware and make sure we're not getting confused what mm is. So there's just a couple different varieties of the ideal gas law, but to be honest, we can just use the ideal gas law and do separate conversions within a question, or we could use these particular shortcuts. So let's look at an example of the ideal gas law. Start simple with how many moles of propane So our question here is how many moles of propane are there in 10 liters or in a 10 liter cylinder at 25 degrees Celsius and 648 millimeters of mercury. So, kind of going through the conditions, we really find that we only have one set of conditions. We have a volume, we have a temperature, and we have a pressure. And we're trying to figure out, our mole value, which we, don't know. So this is obviously pointing us to just the ideal gas law, right? There's no two set of conditions, and that might point us to more of those simple gas law relationships. But in this case, right, there's only one set of conditions. So our volume here being, the 10 liters, our temperature, remember we have to be in terms of units in Kelvin, so we have the 298 Kelvin. Remember our R is the constant, and that's why it's so important to look at the units of the constant, right? Because we have to be in those units in terms of liter, atmospheres, moles, and Kelvin. And then we have our pressure, which we're going to need to do a conversion on with the 648, converting that into atmospheres, or 0.853 atmospheres. And so those are the values now that we can simply plug into the ideal gas law and then solve for the mole value that we're looking for. So we have our pressure of 0.853 atmospheres. We have our volume of 10 liters. We're solving for moles. And so we just need to do our algebra and, divide everything over the 0.082 and the 298, and we get a value of 0.35 moles of the propane. So that's one example, right? Pretty straightforward example with our idea of just using the ideal gas law to get to moles. Let's do another example. So here we have the density of a gas, and that was measured to be 3.62 grams per liter at STP, our standard temperature and pressure. What now is the molar mass of the gas? So here we have, the notion of density. So, as soon as I start to think about or see that, I now start to think about the density form of the ideal gas law. And I have my standard temperature and pressure, which would be involved with STP. So, my temperature would be the 273 Kelvin, and my pressure being the 1.00 atmospheres. We have, the liter atmospheres per mole Kelvin as far as our R value. And what we're asked is for, that molar mass, given the fact that we know the density of the gas to be 3.62 grams per liter. So we can use this, form of the ideal gas law to solve for that molar mass idea. So if we plug those values in, we have our, 1 atmosphere is equal to the density times our R value and our temperature of 273 all over our molar mass. So if we solve for molar mass, really it's just the product of our numerator right over that pressure of 1 atmosphere, and we end up with a molar mass of 81 grams per mole. So that's now using the density version of this expression to solve for molar mass. Let's do a third example before moving on to a new topic. Okay, so here's our question. We have analysis of a gas revealed that it was 14.3% hydrogen and 85.7% carbon by mass. It was also found that 29.4 grams of the gas exerted a pressure of 2.84 atmospheres in a 3.6 liter container at 260 degrees Celsius. What is the true formula for this gas? So this is actually bringing some old stuff into the mix, right? This idea of true formula. Remember that, our true formula is really derived from our empirical formula. Right? Remember, if we take our molar mass of our true and divide it by the molar mass of our empirical, right, we get a ratio which connects the two. And the empirical formula we could get from something such as mass percent, which is what we see above with these 14.3 and 85.7% values for elements of carbon and hydrogen. So we have that aspect. It is probably some aspect is getting to 1, right, which would be the empirical formula. Now, to get to the true formula, we would need to have the molar mass for the true form. And if we look at the data in the question, we can get at that molar mass from these other pieces of the puzzle. That 29.4 grams of the gas exerted a pressure of 2.84 atmospheres in a specific volume of 3.6 liters and at a specific temperature of 260. So the second would be using, right, the ideal gas law to solve for our molar mass. And then we can put that all together as far as step 3 to really get to the true formula. So step 1 here should be old stuff, right? We assume 100 grams. So percents, turn into mass values. So if we have, 14.3 grams of hydrogen, and we're dividing by 1 gram per mole, we get 14.3 moles of our hydrogen component. And if we take our 85.7 grams of the carbon, divide by its mole value, we get roughly like 7.1 moles of our carbon. So we would say that's C 7.1, H 14.3. We divide by our 7.1 value, and roughly we get, C1, H2. Now that is our empirical formula, right? And so that's what we're doing in step 1, is getting at that empirical formula. Also, we have, the molar mass of that as well. Mainly, roughly 14 grams per mole. So that leads us on to step 2, which is now utilizing, the ideal gas law representation. Namely that we have PV is equal to mass times R times T over molar mass. And realize that this would be the true molar mass, given that this is an actual experiment to determine that. So if we start to plug our values in, we have our pressure of 2.84 atmospheres, our volume of 3.6 liters, we have our mass of 29.4 grams, our ideal gas law constant, and then our temperature, which would be 533 Kelvin, right? Keep in mind that our temperature was 260 degrees Celsius plus our 273, so that's where that value comes into play, or comes from. And then that's all over what we're actually looking for, which is the molar mass of the gas, or that true molar mass. So if we rearrange it, we would pretty much see the same thing in the numerator after we take the reciprocal to get molar mass in terms of solving for it. And so if you were to track units, everything here would cancel out except for our grams per mole, and we end up with a value of 126 grams per mole. So that was step 2, putting now the ideal gas law relationship together to get at the actual true molar mass. So step 3, we're trying to figure out the ratio, which is, remember, the true over the empirical in terms of molar mass, and we have 126 grams per mole divided by 14, which is equal to a 9-to-1 ratio. So we had CH2 as our empirical formula. We're now multiplying through that formula by 9, and we end up with C9H18, and that is our final answer. That is the true formula. So that is the gas laws, the simple gas laws and the ideal gas law. Really only one ideal gas law, but then these subtle other variations that we've talked about. If you consider all the examples that we've done so far, these are all pure gases where we just have one gas and being involved. Obviously, we have mixtures of gases as well. For instance, the room we're in now, it's a mixture of nitrogen and oxygen and carbon dioxide, water vapor, hopefully no methane. But, it is manure season out here in Vermont, so definitely smells a little bit like methane out there in my neck of the woods. Any rate, what about mixtures of gases? So that's where we're going to next.